Have you ever wondered what happens when an object gets sucked into a black hole? These enigmatic entities are the universe's ultimate vanishing acts, a place where the laws of physics as we know them cease to apply. Today we're taking a cosmic deep dive into the captivating world of black holes. These are not just spaces of nothingness, but indeed they are places of immense gravity, so intense that nothing, not even light, can escape their grasp. Black holes come in a few different sizes, but they all share certain characteristics. There are stellar black holes, the remnants of massive stars that have collapsed under their own gravity. These celestial bodies are roughly 10 to 20 times the mass of our Sun. Then there are the intermediate black holes, which are typically tens of thousands of times the mass of our Sun. Scientists are still unsure how these form, but they could be the result of stellar black holes merging. Lastly, we have the supermassive black holes, the true behemoths of the cosmos. These giants are millions, sometimes billions of times the mass of our Sun, and are typically found at the center of galaxies, including our own Milky Way. But what's truly fascinating about black holes isn't just their size. It's the way they warp and distort the fabric of space and time itself, creating environments where our standard laws of physics simply do not apply. So what happens when an object gets too close to a black hole? What lies beyond the point of no return? And how do these cosmic phenomena affect the universe around them? These are just a few of the questions that have intrigued scientists and astronomers for decades. And today we're going to attempt to unravel some of these cosmic mysteries. To understand them, we first need to grasp the basics. So buckle up and get ready for a journey to the edge of the known universe, as we delve into the enigma that is the black hole. At the heart of a black hole lies a gravitational singularity. Now that's a mouthful, isn't it? Let's break it down. Imagine a point in space where gravity is so intense that it warps and twists everything around it. It's like the ultimate cosmic blender, distorting the fabric of space and time. This is the gravitational singularity, a point of infinite density that sits at the very center of a black hole. It's where our understanding of physics, well, takes a nosedive. The laws of nature as we know them simply stop making sense. The singularity's immense gravitational pull bends light and slows time, leading to some mind-boggling consequences. For example, if you were to approach a singularity, someone watching from afar would see you slowing down, seemingly frozen in time. Yet for you, time would pass normally. It's a strange and fascinating concept, isn't it? Time and space as we know them break down, creating a cosmic conundrum. Surrounding the singularity is the event horizon. Now, if you're thinking this sounds like something out of a sci-fi movie, you're not too far off. The event horizon is a real-life boundary in space-time that plays a crucial role in the enigmatic functioning of a black hole. Imagine it as the ultimate point of no return. Once anything, be it a stray star or a rogue photon of light, crosses this boundary, it's destined for a one-way trip towards the singularity. The event horizon is the black hole's cloak, hiding its inner workings from the prying eyes of the universe. Here's where it gets even more interesting. The event horizon isn't a physical barrier. You wouldn't hit a cosmic brick wall. Instead, it's a point where the rules of the universe as we understand them start to warp and twist in unimaginable ways. Anything that crosses this boundary is destined to be swallowed by the black hole, disappearing from our observable universe forever. One of the bizarre effects near a black hole is spaghettification. As this term might suggest, it's not about making Italian cuisine in space. Rather, it's a process that occurs when an object gets too close to a black hole. Imagine, if you will, a spaceship venturing too near. The gravitational force at the closest end would be so much stronger than at the farthest end, causing a dramatic stretch in the spaceship. This differential or tidal force would elongate the spaceship, making it resemble a strand of spaghetti, hence the term spaghettification. It's not just spaceships though. Even stars can be spaghettified if they wander too close to these cosmic monsters. Spaghettification is a brutal reminder of the immense power of black holes. It showcases the extreme conditions and the strange realities that exist beyond our planet. It's a cosmic noodle-making process that defies our everyday understanding of physics. Now, let's talk about the mind-blowing concept proposed by the legendary Stephen Hawking. Hawking radiation, a term that has revolutionized our understanding of black holes. You see, black holes have long been considered the ultimate cosmic dead ends, a one-way ticket into oblivion. But Stephen Hawking, with his brilliant mind, proposed a radical idea that challenged this notion. He suggested that black holes might not be as black as they're painted. To understand this, we need to delve into the realm of quantum mechanics, the physics of the very small. Here, particles and antiparticles are constantly popping in and out of existence in pairs, a phenomenon known as quantum fluctuations. Now, when this happens right at the edge of a black hole's event horizon, something extraordinary occurs. One particle falls into the black hole, while its partner escapes into space. The escaping particles are what we call Hawking radiation, but there's a twist. The energy to create these particle-antiparticle pairs can't come from nowhere. It's borrowed from the gravitational energy of the black hole itself. So, each time a particle escapes, the black hole loses a tiny amount of its energy, and consequently, its mass. Over unimaginably long periods, this process could cause a black hole to lose so much mass that it evaporates completely. This concept of black hole evaporation was groundbreaking. It painted black holes not as eternal cosmic prisons, but as entities that can change, evolve, and even die. So, what does this mean for us? Well, it means that black holes might not be the absolute endpoints we once thought they were. It means there's still much to learn about these enigmatic cosmic entities. And most importantly, it means that even in the darkest corners of the universe, there's a glimmer of light. Black holes aren't completely dark. They emit faint radiation due to quantum effects near the event horizon. The existence of Hawking radiation leads to the information paradox. This paradox is a cosmic conundrum that has puzzled scientists for decades, and it's all about information. Now, when we talk about information in this context, we're not talking about knowledge or facts per se. Rather, we're talking about the fundamental data that defines the physical state of a system. It's the DNA of the universe, so to speak. Consider this. Every particle that makes up everything in the universe carries a certain amount of information. This information includes properties like mass, charge, spin, and so on. It's this information that governs how particles interact with each other, essentially shaping the universe as we know it. Now, let's bring black holes into the picture. According to the laws of quantum mechanics, this information should never be lost. It can be transferred, transformed, or encoded in different ways, but it should always be conserved. This is a fundamental principle of quantum physics, known as the law of information conservation. However, black holes throw a wrench into this well-oiled machine. When something falls into a black hole, it seems that all its information is lost forever, swallowed up by the black hole's insatiable appetite. This appears to violate the law of information conservation, hence the information paradox. But wait, there's more. Stephen Hawking's prediction of Hawking radiation adds another layer of complexity. If black holes slowly evaporate over time, emitting Hawking radiation, what happens to the information they've swallowed? Does it simply vanish as the black hole evaporates, or is it somehow encoded in the Hawking radiation? These are questions that continue to baffle scientists. The information paradox has profound implications for our understanding of quantum mechanics and general relativity, two pillars of modern physics. It forces us to rethink some of our most basic assumptions about the nature of the universe. It's a question that challenges our understanding of the fundamental laws of the universe. The black hole enigma continues to puzzle scientists, and we've only scratched the surface. The mysteries of these cosmic phenomena are as vast as the universe itself. Consider the gravitational singularity, where all known laws of physics come to a grinding halt, or the event horizon, that inescapable boundary, a point of no return. Let's not forget the peculiar process of spaghettification, the universe's own noodle maker. Then there's Hawking radiation, a testament to the brilliance of the human mind, yet it opens up a whole new can of worms, the information paradox. These complexities and contradictions are what make black holes such a fascinating subject. They push the boundaries of our understanding, challenging us to think beyond the realm of the known. So, what are your thoughts on these cosmic mysteries? Remember to hit subscribe for more intriguing space content. Until next time, keep looking up.